So thanks for coming to our talk. Before actually explaining anything, we want to show you like a couple of things that came out just as late as last week, which we think are really interesting. So let's immediately jump into it. So this is Steer AI, which is a website from Ramp Labs, where you can basically build or specify like a concept or a persona, and that persona actually influences how an LLM works. So you can see at the top, I selected Jim Bro, basically because it was like the best, the one that gave me the most satisfying results. And then you give it a prompt, as you do with any LLM. In this case, write me a haiku. And then on the right side, you have the baseline, which is the normal LLM. And on the left side, you have the so-called steered AI, which is like influenced by the persona. And so in this case, it should be like a haiku from a Jim Bro. It's quite fun. It has a typo inside of it. I don't know if that's significant or not. And this is really interesting. On the right side, you have all the concepts that amounted to this persona, to the Jim Bro persona, and that steered the result of the AI. This came out like a week ago. It's not perfect actually, but it's really fun to play with. And then the other more serious, I think, result that we wanted to show is a paper from Anthropic in their blog Transformer Circuits. And this is quite new as well. And they played with emotions, the concept of emotions. They were able to like understand, find some specific, they call them emotion vectors inside the LLMs, and also to steer them as well. So you can see on the left, for example, they had a sentence which is like, I took some amount of a drug, and then they changed that amount from a safe level to an unsafe one, and they were able to record this emotion vector changing in the model. Like with a safe amount, the model was calm, and then with an unsafe amount, this emotion vector like fired up as afraid. And so this is really interesting. Then other related activities, such as posing a question to the LLM, like do you prefer A or B, and then seeing that the emotion was actually changing the output, so the choice between the two activities, so maybe like joyful activities versus like something bad, and they were able to influence that as well. So these are two examples of a really novel way of thinking, or you can say a paradigm shift, which is basically they change the model behavior without changing the prompt. So it's not like prompt engineering, it's like hacking in the model, in the internal activation, in the internal numerical representation of the brain of the model, if you will. It is actually a key shift, and it is something that we're starting to see more and more in these years. We can say like it's reverse engineering of how the model works, and it is like at the heart of this new field, which is mechanistic interpretability. So the idea that we want to interpret what the AI says, because it has many useful consequences, of course, but we want to do it in the most mechanistic way possible. Like we want causation, not correlation. We want to actually see the numbers and be able to tweak them to be sure that the AI does and says what we want to say. So hopefully we're going to explain a little bit of how this was achieved. We will start by saying that, the usual problem with LLMs, and then we will delve more into their structure. There'll be quite a bit of math, but hopefully not too much. We will go into some of the features that characterize the internal representation of the model, and then some of the latest advances, some of more practical stuff. Let's start. So LLMs are opaque, or in other words, they are black boxes. Like there's lots of numbers, there's lots of computation, but we cannot really understand what's going on under the hood. A useful concept is that of the residual stream, which is like a part of the architecture of the model, which is thought as the central communication channel of the model. It's like a flow of computation where all the other components read from and write to. So it's like a if you wish, like a memory that gets updated as the model progresses in a forward path. And so this is where we will focus our attention. So, but first we need some basics. We all know the model processes numbers, right? It has neurons which contain numbers. And when the model is computing something, for example, when you give it an input, it goes on and computes all of this stuff in its attention heads or whatever. I don't know how familiar you are with the technical architecture, but the point is that basically we're talking about linear algebra. We are having a linear vector space composed of neurons. Sorry. C'è una minimizzazione che non funziona. So you can think of these neurons as basically directions in a space. So it's like the horizontal direction, the vertical directions. I will be representing everything in 2 dimensions for obvious, clarity and simplicity. But you have to think there's lots and lots of them. And so each neuron stores a number. So each number is a component of these vectors that live in the vector space. So for example, let's say we have a universe with just 2 concepts, the cat and the hat. And so our model will learn these 2 concepts by encoding them into 2 separate directions in the 2-dimensional space. So it will have if you will, a catness neuron encoding the concept of a cat and a hatness neuron encoding the concept of a hat. So when you say like, I'm wearing a, and the model completes your sentence, it's like, oh, wearing, that means that it's the hat. So it will fire up the hatness neuron, right, and not the catness one. And this is called monosemanticity because each neuron has 1 concept. And it's ideal for us that want to interpret the model because if each neuron has 1 concept, it's easy to look at it and say, oh, that's the hatness neuron. And if you want to suppress a concept because maybe we don't want the AI to say something, we could just suppress that neuron, And this is all fine and good, but in actuality, what happens more often is that, in a linear space, it's not really always the case that the vectors are aligned with the neurons. So it's not just like one neuron is on and one is off, but more often than not, it's a combination of neurons. Like each neuron has a number inside of it, which is not 0. And so, for example, the cat concept may not be one of the 2 neurons, but a combination of the 2. So for example, 0.4 of neuron 1 and 0.7 of neuron 2. And the hat concept will be like another vector. And so what stays the same as before is that the 2 are orthogonal, right? Orthogonal vectors are like the most far that they can be, like the most different that they can be. They don't share anything, they're like perpendicular. And so this is fine, but we are losing like the meaning of the neurons because we don't have the hatness neuron anymore. We have a direction that's not aligned with the neurons, you know what I mean? So, for example, the same picture as before, I have a gray and it's gonna say cat or hat, it doesn't matter, but it's not like the hatness neuron fired up or the catness neuron fired up because the neurons don't mean anything anymore. They mean something only in a certain combination. And so the catness concept is now a combination of the 2 neurons, right? It's 0.4 and 0.7. So if neurons are not meaningful anymore, what are? We call these things, these concepts, features. And they're basically these generic directions in our vector space. Catness, the concept of a cat is a feature, the concept of a hat is a feature. They live in this vector space. They're represented by a combination of neurons, but not necessarily one single neuron, you know what I mean? And this leads to stuff like superposition, which means that we have some direction that may overlap. We have some different concepts that may amount to the same vectors because you're combining neurons together and you can get to the same direction in your space. So the same state of your neurons will lead to the concept of a cat, the concept of a hat, the concept of a car, or some other unrelated concepts. This is called superposition because concepts are like superimposed on the same mathematical structure. And this is, of course, unfortunately, inevitable because the number of concepts that we want to learn is so much bigger than the number of neurons of our model. As much as the model is, big, a lot of neurons, still the number of concepts is so much bigger. Think about, single people. Like the model knows about famous people. Each person is actually a concept, So where does it live? Like where does it store this information? It doesn't have simply enough space, enough mathematical space to do that. And so some concept will superimpose, we have the same mathematical representation or a similar one at least. And this on the other hand, we can see this from the point of view of neurons. Like if a neuron doesn't represent a concept anymore, what does it represent? Maybe it represents many concepts, like a nuanced version of many concepts. So for example, in the same example as before, maybe now the first neuron represents the ability of purring and also the having wheels, which is, of course, does not apply to cats. It applies to cars, but still is the same direction as purring. So it will fire up for cats and for cars. And so this is not really ideal for us to want to understand, because if we see this number, like is the model thinking about cats or cars? We don't know. So what the model can do, we said, like, ideally each concept is an orthogonal vector. So like it's perpendicular to the other, there's no possible way of confusing that, but we don't have enough directions. We have maybe a space of dimension n, but the number of features is so much bigger than n. And so what the model does is try to be as orthogonal as possible. So like, as you can see in this example, the three concepts are like as perpendicular as you can without, making two of them too close in the simple 2D space that it lives in. It is the most efficient encoding that the model can do, like keep them as separate as possible to avoid any type of confusion, but still not completely separate. And this is a nice mathematical interpretation, because while as you scale up your neurons, each neuron is a new direction. So if you encoded concepts with neurons, you had like an extra neurons equals an extra concept. With this almost orthogonality, actually this scales exponentially. So there's a nice theorem that shows that as you increase the number of neurons, the number of almost orthogonal direction actually increases exponentially. And so this means at a certain point, the number of features you can have actually is enough for your reasoning of your model. And this is why the model is so incredibly able to encode a lot of concepts. And of course, this brings a trade-off, because as I was saying, almost orthogonal is not orthogonal. Like, there's still a bit of confusion. The concepts are still a bit close together, right? They're not completely far apart. And so you have stuff like interference, where like the concept of a cat spills a little bit on its neighbors. So it spills a little bit on the hat concept and on the car concept. And then you have confusion, because the same vector, the cat vector, can be made by the cat concept, but also by the car concept plus the hat concept. If you remember a bit how vector addition works, it's like you take the car arrow, you sum the hat arrow, and you get straight into the cat arrow. So this means that you cannot understand if the model is thinking about cats or if the model is thinking about, I don't know, car having hats inside of them, because basically they amount to the same mathematical vector. And this is a trade-off, because you want to be able to store more concepts. So you want to be able to have a lot of these vectors, but then they get closer together, and so you risk confusion. And so all of this begs the question, like, why does that work? And the key concept, we think, it's sparsity. So basically, the idea of sparsity is very intuitive. If you want to describe something, you have to use a feature that specifically describes that thing and not the other ones. Like in a sea of blue objects, the concept of blue is not really useful, right? And so, for example, the concept of being gray with objects that can be gray is not really a discerning factor, whilst the concept of purring is. And so we think that the model actually reasons in and learns in sparse features, trying to encode the most sparse feature that it can. With sparsity, the idea is that basically your concept will be a combination, your object, whatever, a cat, will be a combination of many features, of many concepts, but only a few of them will be actually used at a time, because they are sparse. So like, it's like if you have to describe a cat, you won't say a lot of the stuff that is so obvious and it applies to everything. Like maybe you won't say like it is a living being. You will say like it has whiskers and it purrs. And in the same way, the model will not use features that are basically useless and redundant, but only the fewest amount and the most specific amount it can. So what's going on is that you have all of these concepts in the model's mind, and they are said to form an over-complete basis, in the sense that they are complete because they can explain the whole universe of concepts, but there are too much of them. You don't need all of them to explain something, right? In the way that we talk, like we don't always say everything about something. And so the model will only use them a few at a time. And this is the concept of sparsity. This is what allows the trade-off to be in our favor, because with this, there's less risk of confusion, because when you use a few features, you can be, the risk of confusion is lower. So just a nice, wrap up of this concept. The whole things that I said can be summed up in the what's called the linear representation hypothesis, which is basically what I just said. So that neurons, sorry, let me go back a second. That neurons in the residual stream are like linear combination of these features, of these concepts that the model has somewhat learned. These features are an overcomplete basis in the sense that there are so many, there are too many for the neurons to deal with, and they can describe the whole universe of the concepts for the model. But also they are sparse, so they use like really parsimoniously. And this is a hypothesis, meaning that we're just saying that it is true, but we don't actually know about it. But actually, it's been like tested by basically Anthropic and OpenAI and the biggest players in the sector. I will skip this because we don't have too much time. But so this is an active field of research. We are quite sure about at least some of the bullet points in the hypothesis. We find them plausible. We are partially testing them with toy models and stuff, and so that's why it is important to know that it is a hypothesis, but still it's a working hypothesis. So we will reason assuming that this is true. This is how the model thinks. If we assume this hypothesis, which is hopefully I explained a big if, but if we assume it, then we can do the next step, which is feature recovery. So we just assume that the model has this mind with concepts, which are these vectors, which form an overcomplete basis and blah, blah, blah. We need to find these vectors, because if we find these concepts, then we can hopefully understand better the reasoning of the model and also steer the feature to change how it computes. We won't go into details about this. It's really complex, ongoing field of research. This is called sparse dictionary learning as well. So you have to imagine you're learning like a dictionary, an actual dictionary of concepts, while where instead of the explanation you find in a dictionary, there's just a vector. So like the concept of a cat is this vector, the concept of a hat, it's this other vector. It's a really hard task, because as I said before, the number of concepts is so much bigger than the size of the space they live in, and they're all overlapping. And so what you do usually is you take another neural network, which is called an autoencoder or a transcoder, which maps this space into a much bigger space, and hopefully in this much bigger space, the concept gets disentangled, like they don't overlap anymore. This is again an ongoing field, and it's really interesting, and hopefully maybe next year we're going to be here with some new result about it, because it's really exciting. I will leave now to Luca for wrap up.
Okay. Hello everyone. Okay, this was a tough part, but we're trying to bring everything together finally. All these concepts, monosemanticity, polysemanticity, superposition, feature learning, or feature recovery, all became extremely popular in the past couple of years. And this happened because this thread of research was not invented like yesterday. It has a really long tradition, and we can kind of see the formalization of the idea of this mechanistic interpretability field, like the formalization of it all, starting from 2020, back when we were still doing computer vision models, as Peter was saying in the morning, basically. There were a bunch of papers and milestones throughout the years, but what I would like you to focus on is that in the past, like from 2022 to 2024, what was achieved, especially by folks working in Anthropic, was that they scaled their experiments from toy models and like just one layer long and deep neural networks back to state-of-the-art models, such as various versions of Claude 3 Sonnet, Claude 3.5 Haiku, and even some research on the latest like 4.0 versions of Opus. And so this brought us to a much more interesting point where we can kind of have like stable or sophisticated enough tools to recover features from the neural networks so that they can start building stuff on top of it. And say, for example, that, so just to wrap it up, like the past couple of years of research, we found out that there is some empirical evidence of superposition, of polysemanticity, and then we can do more with feature recovery. And this is basically where we end up nowadays. And the idea is that now that we have, interestingly enough, powerful enough methods to recover features, we are now able to take a look at the models that have these retrieved features and start seeing where they activate and map which neurons activate throughout the whole token stream, which means basically when I'm trying to see the completions that happen for a sentence like the capital of Texas is Austin, we can see which regions of the feature space, the recovered features, not the original neural network, but the one that we learned the features from, fire up and build an attribution graph of what concepts fire up. And this is kind of a like the intuition behind this and the hope behind this, that these regions that are called circuits contain the concept of something. For example, maybe the first, like here in the example, the first column fires up the feature or like the circuit of being a capital, whereas the third one fires up the circuit of Texasness. And the last one, that is for the completion of Austin that we don't see, contains the concept of Austin and being Texas. And given that these concepts all merge up and interact with each other, we see the concept of Austin naturally arising from the neural network. And this basically marks a kind of a turning point where we are starting to make this interpretability field a bit more scalable, somewhat casual in the sense of causality with a huge asterisk, and also actionable. And remember that the end goal is that we can make interpretability an engineering tool to steer the models, not only to understand them. And there are caveats, yes, but the applications are extremely powerful. And this is why we want to pursue this field, not we, like Gabriele and Luca, but like the researchers pursue this. Because we can use those for safety purposes. Instead of saying, please, please, please don't tell anybody how to make a bomb, we can just have like the model dynamically depress the concept of bombs, or use it in the training process to make it move away from that so that such a concept never arises under certain combination of concepts. But we can also do that at inference time, when we are using the model, suppress certain concepts or make the model steer away from trying to hack or just run rm.rf on your machine. And instead of having just like a regex, and then the model just says, okay, maybe I can run this other command to erase all of your laptop. This is also extremely useful in terms of customization, because you can just apply a vector that changes, that steers, that moves the model in a different direction that applies to your user persona or your customer or your use case in general, without you needing to just write a really long system prompt and hope that it works. And finally, it's an incredibly powerful debugging tool, because you can see when you train the models how they behave and which areas fire up. And maybe you want to see, well, maybe the data that I recovered on this part is not really like changing neurons the way I would expect it to, making the model more responsive. This still has lots of limits, the first one being that it's still largely a post-hoc process. So we just assume that there are some features that the model learns, and we try to recover them after the model has been trained. So we're not really just saying, hey, maybe the model learns these features. We try to train a different neural network that hopefully learns what the features are. And we use another LLM to basically tell us, and I'm just doing a huge simplification of this, what this feature refers to. So we're using another LLM to say if a neural network that was trained on the original LLM has like found what concept. So feels fragile, but still allows us to advance the research. And of course, features are still overlapping and are still like ambiguous. So you might have the case that a feature does not identify uniquely a certain concept, but you have many of them that might refer to the same thing. And still, we do not know, especially whether some circuits are fired up, but most importantly, why some others aren't. So for example, when I'm talking about Texas, why, of course, Texas are in capital concepts fire up, but what about other circuits of other cities that do not fire up? Why don't they fire up, right? So the idea is that these circuits still rely on some, like mostly we're really still doing naive stuff, and most importantly, we are not really changing, like arguably not really doing causal interpretation. The model might be just learning correlation stuff, so that might not be true at all, but still we're advancing the research. And this is basically the sum up of this whole situation, is that we are just getting started, but I hope you can get the gist of how enticing this whole field is, how like powerful the applications are, not only in terms of, of course, this is amazing research, but also in the terms of the practical application it has, not only from a customer perspective, but also as a safety tool, a debugging tool. And so right now, neural networks still operate as black boxes. Yes, we are finding tools to try and explain some of it, but we've been accelerating. And poof, there we go, okay. Researchers found some kind of empirical evidence scaling from toy models to much and much larger models of these hypotheses that models build representations of concepts that are more and more advanced the deeper you go through the neural network. And so that the lower layers learn maybe the semantics of a language, whereas the latest layer learn how to write fluently in a certain language, whereas the middle layers learn the concepts and where to intervene to alter those concepts. And finally, they're starting to find empirical evidence of some behaviors that influence the model, such as what Anthropic did, like last week, forcing us to change the whole presentation, is that these emotional patterns as the model finds, you can find when the model generates some text and you're like, oh, why is it like answering like in this nice manner? What is always saying, no, you're absolutely right. That's because there's some like, not really causal, but there's some mechanical interpretation, mechanical features that trigger when you're working on rewarding stuff, when you're challenging it, that makes up like a functional pattern that make it work, like produce better code. That's not an emotion, because the model does not learn emotion. That's a different thing from displaying emotion and knowing what emotion are. But still, we are trying to, they're starting to understand what fires up and what's happening inside and potentially steer it. This was all of it, and I know it's been technical, but if you have any feedback, we'd love to get in touch with you and share it. Thank you very much.